So this is video number 5 in this series on analyzing the MR angiogram data from the MSc project that this team is working on. In this video, I want to tackle 2 different sets of ideas that are going to be quite useful no matter what specific question you're interested in. One is trying to break down this complicated looking vascular tree into smaller chunks in some reasonable way. And one idea here is to try and divide different sections of the arterial tree depending on which part of the brain they actually supply. So this leads us to this idea of territories. And you can actually search for territory maps for the anterior, middle, and posterior cerebral arteries. There's lots of tissue resources available. Lots of information is known because of the stroke research and so on. In fact, I found one paper that includes as part of their data set an atlas, sort of a label image of the different territories broken up by which vessel they come from and left and right, conveniently in MNI space. So the first task is going to be bringing that MNI template, this template in MNI space, back into our original data set so we can try and segment out different sections of this MR angiogram that we have for one particular subject. So I'll use FSL and the alignment tools there to do that. And then the second bit, which I'll leave for the next sort of section of the video, so video 5.2, I guess, is to try and understand what the actual structure of this arterial tree is, how things are connected. And one of the ideas that's going to be useful to sort of look into here is how to skeletonize the images that basically try and identify what is the essence of the structure. And so you can look up skeletonizing, which is sort of an image processing operation that's often used. And then we can actually turn this into a graph, which is sort of not a graph as in a time series plot of some data, but a graph in the sense that the mathematicians talk about, where we have vertices or nodes that are connected by links. And so there's some MATLAB functions, MATLAB code that people have already written, and I'll try and download those and apply them to the dataset we have. Okay, so but for the first bit, let's go into the terminal here. These are the files that you already should have from the previous video. The only other thing that's new here is this MNI vascular territories file, which I downloaded from this particular link here. So let me just try and open that so you can see where that is. And you can see here, there's a whole bunch of files available here. The one I downloaded and provided in our shared folder is this vascular territory map, which you can look at in a second. Okay, that's this file. It's a small file. You don't need to download this again. We've already got that. So the idea here is this is at a certain resolution, maybe 1 or 2 millimeter voxel sizes. Let's find out. So I use FSL info to find out what the voxel sizes here are. Pixel dimensions are 1 by 1 by 1 millimeters. This is 1 millimeter isotropic data. But if we look at the sizes of our angio brain scan, you'll see that within plane we have much smaller voxels. So what we want to do is we want to register this image, which is this vascular territories file, into this space here. All right. So let me just clear the shell here and show you the files again. From a previous step where I've mapped this angiobrain into the MNI space, I have this matrix, this X form, that tells me how to move from our native space of the original data acquisition into MNI space. And so I want to actually go backwards. So I need to know how do I go from MNI space back into the original space. So what we need to apply is an X form or matrix that's actually the inverse, the backward step from this here. So we need to convert this first. I'm going to first load up the FLIRT GUI. which you can launch directly. And I'm going to use one of these utilities here, which is to invert one of those transforms, which allows me to do this step. So here I'm going to take this transformation matrix going from A to B, and I want to essentially have the matrix that will take me from B to A. So there's only one matrix available here, so I'm going to pick that one here. And to go backwards, I will call this MNI to angio in this particular case, to notify that, basically that it's signify that we're going backwards. I'm going to do that. Press the button here, press go. You'll see the command launch and being done in the background. So I can close this window. And if I now list the files, we now have a second mat file, which is the one, MNI to angio. So I actually wanted to call this MNI to angio mat. So I'm moving this file, or I'm basically just renaming it to something that contains the mat file. Okay, so there's no confusion later on. So we've got that file now. So I can go back to FLIRT now, and I can apply this transformation that allows us to go from MNI space into the native space, and I'm going to apply it to this vascular territory map that I've downloaded from the internet, and I will turn that image into one that is in the native space. So these two images are can be overlaid nicely, and if we load them in MATLAB, the voxel grid in those two images will be exactly the same, and you'll see how that's useful in the next step when we actually try and use that information to break up the image, the MRA image that we have for our single subject, into different chunks according to which territory they supply. Okay, so that's another utility, which is we actually want to apply a FLIRT transformation. So in this case, it asks me what's the direction of the trip I want to take. So the transformation matrix is the one we've just created. So I want to go from MNI to angio space. I want to give the input volume, which is the one we're trying to transform. So that is this vascular territories file that I've downloaded, because that's the thing we're trying to actually turn into something else. And I'm going to base the output size onto an existing volume, essentially in the destination space, which is the angio brain image that we have. So this is the one where the in-plane voxel size is much smaller. So I'll use that. The output volume I'm going to call to mirror the MNI vascular territories. I'm going to call that angio underscore vascular underscore sorry, still got the cough. Now, under the advanced options, I want to make sure that in this label image, voxels will be labeled according to a number 1, 2, 3, 4, and 5, which signify a particular kind of territory. So 1 might correspond to the left side for the anterior cerebral artery, and so on and so forth. So when I resample these images, I don't want to end up with some interpolation artifacts and end up with numbers that are 1.2 or 1.3, because they don't really mean anything. Okay, so I need to control how the image is actually being transformed into this destination space. And the choice here is nearest neighbor, because we want to guarantee that each voxel in the destination space can only ever get a value that was present in the original image. Okay, so if you've got a question about that, that's something for the interactive session. Maybe ask me to go over that again if you want. Okay, so I'm going to press the go button now. You can see here's the command that runs in the background. And so while this is running, what we're hoping for is that this MNI vascular territories file will be transformed in the original angio space. And so we have a one-to-one correspondence of these images. And in the next step, what we're going to do is we're going to isolate parts of the image that have a particular index value in the in this territories file, and we're going to only select those bits out of our original data set. Okay, but before we do that, let's first have a look at what's now present. So I'm in one, let me just control L. If I do ls minus t, or lt, then you can see, oh, I misspelled here, but it's fine. I'll be able to see that. You can see them when the files were created. So these are the most, and they're sorted according to when the most recent one up top. So this is the one that was just created. This is the matrix file that we created before. Right, let's superimpose them. FSL fossilize. So what I'm trying to see is whether the original angio file, angio brain, if I superimpose angio vascular file, and let's do a color map random, which is a particular color map. I'm going to pick an alpha value of 50, and let's hopefully be able to see what's going on here. Okay, so this colorful image that you see on the top is this atlas that tells us the different territories that are supplied by the different arteries, divided up by left and right. So if I hover, for example, over here, and you look at the value that this takes, so this is the number 2 here. If I go into the blue one on the next side, that's the number 12. So these are, wherever there's a 12 present in this image, is a location that's provided by this particular blood vessel, right? And you can see that's shared here. And so the idea I had for this is we're going to try and identify, say, only the yellow bits in the image and carve up the original underlying image, which is the one you can see here, this guy here, which, if you remember, if I change this to 1500, only contains the blood vessels. Oh, actually, that's a little bit hard to see. Maybe go to 5000, make them a bit brighter. So these are the blood vessels, right, here that you can see. If I superimpose this guy back on again, we can try and find out which parts of this underlying image is present in this yellow blob, in this blue blob, in the other blue blob, in this red one, and so on and so forth. Okay, so there's a way in which we can actually do this using one of the command line tools, so I want to do that next. Right, so this looks like it may have worked. So one other reality check we can do is, maybe you want to think about this, how could I try and establish whether this territories file, this angio territories file, and the angio brain file are likely to be in the same space? What are some of the necessary conditions that would tell you whether these two things are in the same space? So I'll give you a second to think about this here. All right, so one thing that should be the case for sure is that the voxel sizes are the same. Okay, so if I type FSL info and I look at the angiovascular territories image, I should now see that for this file, the voxel sizes are pretty much the same as, or not even pretty much, but exactly the same as this, which looks right. And I could also check that the matrices that are stored in the headers are the same, but it's a little bit sort of more advanced stuff. But hopefully you can see that the dimensions of those two images must match exactly, otherwise we don't have a one-to-one correspondence between these images, which might cause some problems. Okay, so this looks like it worked. So the next thing I want to do is, I want to think about a way of identifying only parts of the image that are in this territory files that have a particular value. Say, for example, the value is 6. So the way to do that is to use this fslmaths program. So in order to get help for the fslmaths command, you can just type fslmaths without any input arguments, and you can scroll through. hopefully we'll have had a look at this program before because it's very useful. And so if I scroll up, you'll see some of the options here that might be useful for us is this idea of masking something. So this is take information from one image and only allow parts of another image through where the value of the masked image is bigger than a 0, usually like a 1 or something like that. The other thing we could do is we could use the thresholding option. So anything that's bigger than a certain value gets zeroed out, or anything that's smaller than a certain value gets zeroed out. And so my idea here is I'm going to try and add a little diagram so you can see that while I'm talking about this after recording this video, is I'm going to take the image that has all these different index values in it, and I'm going to threshold it with an upper threshold first. So using the option U threshold, so which zeroes anything above a certain number, right? So for example, if I only want to allow values of 6 to survive, I could maybe threshold with 6.1 or 6.2, which means 7, 8, 9, and 10 get knocked out, they get set to 0. And then following that, I can threshold anything below a certain number. So I pick a value that's just below 6, maybe 5.9 or 5.8. That would mean that 5, 4, 3, 2, and 1 would also get set to 0. And the only thing that survives is voxels that contain the value 6. Okay, so let me break that down into little steps here. So I'm going to Control L. I'm going to say fslmaths. I'm going to take this angio territories file, vascular, I called it, territories, and I'm going to say upper threshold, U threshold, and I'm going to pick 6.2. And then immediately afterwards, I'm going to threshold it, the resulting image with a lower value of 5.8. And I'm going to say only 6 mask. Okay, and see what happens with that. So this is going to create an image that has the same dimensions as this one, but has been transformed with these steps in sequence. Okay, and it's actually important that they get run in the right order. You can sort of try and convince yourself that that's the case. If you threshold this first and then the other, I think you might end up in trouble. But maybe work through this with a diagram. Okay, so I'm going to look at this only _6 mask image, and what I'm expecting to see is only parts of the original image that had the value 6 and nothing else. Okay, so there should be a white blob surrounded by zeros, and everything in that white blob should have the value 6. Okay, so that's worked perfectly fine. Okay, and so now I have created from this template, which contained all of the different numbered images together, one template that only contains areas that were labeled with this one particular number. Okay, so I could have also done this in MATLAB, but this is sort of a nice way of doing it in FSL in the command line. So how can I make use of that information? So if I Control C will kill this. I can now actually apply this mask to the original angio brain image. Okay, so how would I do that? I would say fslmaths. The input image is angio brain. I'm going to say I want to mask it with a particular file. And if you look at the documentation, it said anything that's bigger than the value 0 is going to be used as sort of as an inclusive thing. Everything that is 0 will get knocked out. So I can actually use this image that I've created just as it is. Okay, I'm going to say only 6 mask, and I'm going to say angio brain, and I'm going to call it 6 just to signify those locations. Okay, and so I'm going to hit return. And while this is going, maybe you want to think about what you now expect in the resulting image to be present. Okay, let's start the viewer. So do you have in your head a model of what we're expecting to see? Maybe think about this for a second. Pause the video if you want. So what I'm expecting to see, if there wasn't an error, is the original image that we had, but only in those locations where this number 6 was present in this mask image. So actually it will have only a selection. It's like a cutout of the original image. Okay. Okay, and so if I actually change the values here, maybe make this range a little bit smaller to make them a bit brighter, you should now see we've essentially cut out a part of the original scan, but only in those locations where this is there. Okay, and so this is a way, by now going through this process again, maybe for the value 4, 5, 12, 11, 13, whatever you want, breaking this big image up into smaller pieces. Okay. So hopefully you see the parallels between this way of doing things and the idea of logical indexing in MATLAB. You could also have implemented this particular sort of breaking the big image up into smaller chunks in some MATLAB code if you prefer. Either one is fine, whichever way you find easier to deal with. Okay. So in the follow-up video to this, I'm going to jump into MATLAB, and what we're going to do in this that particular video is try and break down the arterial tree into its structure, how things are connected and whether connections between certain parts are intact. Again, this will lead us to this idea of skeletons and graphs.